Level 1, Mechanical Explosions. The simplest kind of explosion does not require any burning at all. A mechanical explosion happens when pressure builds up inside a container until the material holding it can no longer resist the force. When the container suddenly breaks, the compressed gas or liquid inside expands rapidly, pushing the surrounding air outward and throwing fragments of the container away. A familiar example would be an overpressurized tank or sealed vessel. The energy was already stored in the compressed material before the rupture happened. The failure simply releases that stored energy very quickly. This is why the word explosion does not necessarily mean fire. What defines an explosion more generally is a sudden release of energy that causes extremely rapid expansion. That expansion produces a pressure wave, which travels through the surrounding material. The faster the pressure changes, and the more energy that is released, the stronger the resulting wave can become. Level 2, Deflagrations. A deflagration is a type of chemical explosion in which a reaction spreads through material at less than the speed of sound in that material. Combustion moves from one region to another mainly because heat from the reacting material ignites nearby material. Ordinary flames are usually examples of deflagration. However, when the same basic process happens inside a confined space, expanding hot gases can create a rapid increase in pressure. The result can become an explosion. The important feature is that the reaction front itself remains subsonic. The pressure created by the expanding gases can still be dangerous, but the reaction does not propagate as a shock wave. This makes deflagration fundamentally different from detonation, even though both may look like extremely fast burning from the outside. In chemistry and engineering, the speed and mechanism of the reaction matter more than the appearance of the flash. Level 3, Dust explosions. Dust explosions demonstrate that materials do not need to look explosive in order to burn extremely quickly. A large solid object usually burns only at its exposed surface. If the same material is divided into millions of tiny particles, however, the total surface area exposed to the air becomes enormous. When a combustible dust becomes suspended in air, many particles can react almost simultaneously. The rapidly expanding hot gases can produce a strong pressure wave, particularly inside an enclosed building or industrial system. Materials such as grain, sugar, wood, coal, and some metals can produce combustible dust under certain conditions. The solid material itself may normally seem harmless. The danger comes from the combination of very small particles, air, and rapid combustion. This is why industrial facilities that generate fine dust require careful control of accumulation, ventilation, and ignition hazards. Changing the physical form of a material can dramatically change how quickly it releases chemical energy. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. Level 4, Vapor Cloud Explosions. Liquids that evaporate can sometimes create a different type of hazard. If a large quantity of flammable vapor mixes with the surrounding air, it can form a vapor cloud. If part of that cloud begins burning, the flame may travel through the mixture, rapidly heating and expanding the gases. In an open area, much of that pressure may escape into the surroundings. In a crowded industrial environment containing walls, pipes, machinery, and other obstacles, the flame can become much more turbulent. Turbulence can make combustion happen faster, increasing the pressure produced by the event. This is an important idea in explosion physics. The same chemical mixture can behave very differently depending on its surroundings. Geometry matters, confinement matters, and the way gases move through an environment can strongly affect how quickly energy is released. A vapor cloud explosion is therefore not simply a large fire. It is a rapid combustion event in which expanding gases generate a significant pressure wave. Level 5, BLEVs. A BLEV is a boiling liquid expanding vapor explosion. It can happen when a pressurized container holds a liquid at a temperature above its normal boiling point. The pressure inside the container keeps much of the substance in liquid form. If the container suddenly fails, that pressure disappears. Part of the hot liquid can then boil almost immediately, producing a huge increase in volume as liquid becomes vapor. The rapid expansion creates a powerful mechanical explosion. The stored energy here comes partly from pressure and partly from the thermal energy of the hot liquid. If the material involved is also flammable, combustion may occur afterward, creating an additional fire hazard. But the basic BLEV mechanism does not depend on combustion. The physical phase change from pressurized liquid to expanding vapor is enough to produce the explosion. This makes BLEV an interesting combination of thermodynamics and pressure physics rather than simply another form of fast burning. Level 6. Detonations. A detonation represents a major change in how an explosive reaction moves. Instead of a flame front traveling below the speed of sound, a detonation is driven by a shock wave traveling through the reacting material at supersonic speed. The shock compresses and heats material directly in front of it, causing additional reaction, which then supports the shock. The two processes reinforce each other. This allows the reaction front to move extremely rapidly through the material. The sudden energy release produces very high pressures over a very short period of time. The pressure wave then enters the surrounding air as a blast wave. Close to the source, the pressure can rise almost instantly before falling again as the wave moves outward. As the wave expands across a larger area, it loses intensity. This is why distance matters so strongly in blast physics. The energy is spreading through an increasingly large volume. A detonation is therefore not simply a bigger deflagration, the underlying physics is different. One is primarily flame-driven, while the other is shock-driven. Level 7. Nuclear explosions. Chemical explosions release energy by rearranging electrons and chemical bonds. Nuclear reactions operate at a much deeper level. Instead of changing how atoms are connected, they change the nuclei of the atoms themselves. Nuclear binding energies are enormously larger than ordinary chemical bond energies, which is why nuclear events can release so much more energy from the same amount of material. In nuclear fission, a heavy atomic nucleus splits into smaller nuclei. The final products have slightly less total mass than the original system. That missing mass has been converted into energy according to Einstein's equation, E equals mc squared. A nuclear explosion releases energy in several forms. An intense blast wave compresses the surrounding air. Thermal radiation transfers large amounts of energy as light and heat. Ionizing radiation can also be produced, and radioactive materials may remain afterward depending on the event. Nuclear fusion can release even more energy per unit mass than fission. In fusion, light atomic nuclei combine into heavier nuclei, again converting a small amount of mass into released energy. This is also the process that powers stars. Level 8. Stellar explosions. At the largest scales, an explosion can involve an entire star. A supernova can release an amount of energy so enormous that, for a short time, one exploding star may become extraordinarily luminous. But the mechanism is completely different from a chemical explosion on Earth. In one major type of supernova, the core of a massive star eventually runs out of the nuclear fuel needed to support itself. Gravity is constantly trying to compress the star inward. For most of the star's life, pressure generated by nuclear reactions helps resist that collapse. When the core can no longer provide enough support, gravity suddenly wins. The core collapses extremely rapidly. Matter reaches extraordinary densities, and enormous quantities of energy are released. A shock can travel outward through the star, ejecting much of its material into space. Another type of supernova can occur when a white dwarf undergoes runaway nuclear burning, disrupting the star. These events manufacture and distribute many of the heavier elements found throughout the universe. Material thrown outward by ancient stellar explosions later becomes part of new stars, planets, and eventually living organisms. At an even more extreme level, some exceptionally energetic stellar explosions are associated with gamma-ray bursts. These events can release tremendous amounts of energy in narrow beams of high-energy radiation.